Okay, in this question we're given a curve, and the curve has equation y is equal to 2x add 3 in brackets all multiplied by e to the power of negative x. Find the exact coordinates of the stationary point of the curve. Stationary point is when the gradient is 0, so we want to differentiate this and solve the equation dy by dx is equal to 0. So let's do that. Our function is 2x add 3, okay, so for part A, y is equal to 2x add 3 e to the power of negative x, and we want to differentiate this. Straight away you should be seeing that this is a function of x here and this is a function of x here, and they are two functions of x multiplied together, so you should be thinking straight away the product rule. So define your u to be equal to 2x add 3 and your v to be equal to e to the power of negative x, so that your u dash, you differentiate this, is going to be 2, and your v dash is going to be negative e to the negative x. Then you state your product rule. dy by dx is going to be equal to uv dash plus vu dash. Always state the rule you're using for the examiner. So this is going to be these two multiplied, so 2x add 3 multiplied by e to the negative x, which I'm just going to write, I'm going to put the negative here and the e to the negative x there, just for simplicity, and these two multiplied together, so plus 2e to the power of negative x. Now, so that's dy by dx. It might be nice and useful to factorize this to tidy up a little bit. So dy by dx, what I'm going to do is I'm going to factorize out the common factor of e to the negative x. There, so I'm going to factorize this, so e to the negative x, and what would I get? Well, I'd have 2 from here, and I'd have take away this thing. Take away 2x add 3, like that, which if I tidy it up, e to the negative x, and this would be take away 2x, take away 3. So 2 take away 3 is negative 1, and we've got negative 2x. So negative 1, negative 2x, like that. So that's my dy by dx there. And find the exact coordinates of the stationary points. So stationary points, dy by dx equals 0. Okay? So for stationary points, dy by dx is 0. So I'm solving dy by dx is equal to 0, i.e. this thing here. And e to the negative x can never equal 0. So this cannot equal 0 because the e to the negative x graph looks something like that. Okay, and the e to the negative x graph does not look like that at all. It looks like this. This type of thing here. And that never actually touches 0, so you get no solutions. The only thing you get a solution from is this. So negative 1 subtract 2x is equal to 0. And if I solve that, I get myself that x is equal to negative a half. So what did it want? It wanted the exact coordinates. Now I've got x is negative a half. I need the y coordinate with that. So y is equal to, it's 2x add 3 e to the negative x. So y would therefore be equal to 2 times negative half is negative 1. And negative 1 add 3 is 2, so it would be 2e to the power of negative a half, which is just a half. So the coordinate of the stationary point is negative a half, 2e to the half, as follows. Okay, next part, it says, we found the exact coordinates of the stationary point. The curve crosses the y-axis at point P. Find the equation of the normal to the curve at point P. So, it crosses the y-axis, so let's deal with this. So let's go down here for part B. Crosses y-axis. Let's think about when a curve or whatever crosses the y-axis, something like this. It crosses the y-axis here, and it's where x is equal to 0. So what we're going to do is we're going to put in x is 0 to the curve. Now let's write our curve down again. It might be easiest if I actually just take a little photograph of that so I remember it. Okay, so that's our curve. So when x is 0, y is going to equal 2 times 0 is 0 plus 3, so 3. E to the 0 is just 1, so it's going to be 3. So our coordinates are 0, 3 for it crosses, and we want to find the equation of the normal. So let's work out the gradient of the tangent first of all. Now we've got dy by dx here. Our dy by dx is this expression here. So we want to work out dy by dx let's just write down what dy by dx was again. E to the negative x, e to the negative x, negative 1 subtract 2x. And we want dy by dx this time at x is 0. So dy by dx when x is equal to 0, e to the 0 is 1, this would just be 0, so this would be negative 1. Now that's the gradient of the tangent, therefore gradient of the normal is a negative reciprocal, which would just be 1. So the equation of our normal is y subtract y1, y subtract 3 is m, which is 1, x subtract 0. So therefore y subtract 3 is equal to x, or y is equal to x add 3. That is the equation of our normal, and we've done it for 2 simple marks there. It says the normal to the curve meets P again at Q. It meets, the normal to the curve at P meets the curve again at Q. Show that the x coordinate lies between negative 1 and negative 2. So what we're trying to solve here, that's for part C, we have our original function, which is 2x add 3 e to the minus x, so 2x add 3 e to the negative x, and we've got our normal, which is y is equal to x add 3. We're trying to solve when these two things are equal to each other, so we're trying to solve 2x add 3 e to the negative x is equal to x add 3. That's what we're trying to find. So we know that they meet at P, but we want to find the other coordinate where they meet at Q. So if we're trying to solve this, it's asking us to show it lies between negative 1 and negative 2. We're going to define a new function, let's call it g of x, to be this one, take away this one, take away this one, like the whole of that one, like that, and we're going to substitute in the negative 1 and negative 2 into that and show this has a change of sign, so g has a root, so these two have an intersection between negative 2 and negative 1. Okay, so going back up here, so what we're going to do is we're going to work out g of negative 2 and we're going to work out g of negative 1. Okay, let's tap those in the calculator. So let's say 2x add 3 close brackets e to the power of negative x. Come out of that, subtract open brackets x add 3 close brackets, and we're going to calculate that at negative 2. And we get negative 8.4, let's call it. So this is going to be equal to negative 8.4. Let's do this again here where we calculate and we say at negative 1 and we get 0.72. So we get 0.7, let's call it. So there's a change of sign. So therefore, change of sign, and as g is continuous, you have to state this, continuous. The reason it's continuous is every function that's part of it is continuous, and g is continuous. G has a root in interval negative 2, negative 1, like that. Therefore, and what we try, just read up what we're trying to show here, Q lies between negative 1 and negative 2. So therefore, Q lies between negative 2 and negative 1, as follows. Okay, going up here, use the iterative formula as follows to get the values for x1, x2, x3, x4. Give x4 to 2 decimal places, show that x4 is the x coordinate of this. So I'm just going to take a photograph of that, and it tells us to start off with negative 1. Okay, so it gives us the iteration. It doesn't ask us to show this at all, which is good. So this is part D. But it says to start off with x0 is equal to negative 1. So get your calculator out. And actually, let's just double check. It wants us to do x1, x2, x3, x4, and it gives the value of x2 to 2 decimal places. So type in the calculator this function here. So, actually, no, the first thing is type in negative 1 equals. So it stores it in the answer capacity. And then type in fraction. 3, subtract 3, e to the power of aunts. So put aunts like that over e to to the power of aunts. Come out of that, take away 2. So you must do it like that so that the calculator remembers my -1 that I want to put in at first, and then every time it works out an answer, it puts that back in to this iterative equation. So I press equals there, and I get negative 1.1619. So I get x1 equals negative 1.1619. 0049, so 0049. x2, press equals again, negative 1.22181, so negative 1.22181, 0241, 0241. Press equals again, negative 1.24, so x3 equals negative 1.24, 0782, 0782, 656, 656, negative and x4, negative 1.2464, so negative 1.24, negative 1.2464, 77652. 77652. Now let me just look up at the question and just double check I've done it right. It wanted x1, x2, x3, x4. It gives the value of x4, give the value of x4 to 2 dp. So I better state x4 to 2 decimal places. So therefore, line after the second decimal place, so x4 would be equal to negative 1.25 to 2 decimal places, like that. Okay. And then for the next part, it says show that your value of x4 is the x coordinate of q correct to 2 decimal places. So we have ourselves, our answer x4 is negative 1.25 here. And I'm going to check a little bit higher, the upper bound, I'm going to check negative 1.245. So I'm adding 0.005 on, and I'm going to take away 0.005 off. So I'm going to check here negative 1.2505. So I'm going to check when I put those two values into my g of x function up here. So I'm going to work at g of negative 1.2505, and I'm going to work at g of negative 1.245. Just notice a tiny little mistake. I don't know why I wrote this. This should have just been 5, like that. I don't know why I didn't do that. So that should have been a 5 there, like that. Okay, I'm going to work those two out. So get your calculator out. You're going to have to rewrite this original g function here. So you're going to have to write brackets 2 x add 3 close brackets e to the power of negative x. Come out of that, take away, and then x add 3 close brackets, like that. I'm going to work it out at negative 1.255, and I get negative 0.03, so I get negative 0.03. If I work it out at negative 1.245, I get negative 0.02. So I get not negative, 0.02, just like that. So therefore, change of sign, g continuous, therefore root between negative 0.0255 and negative 1.245. Therefore, q equals negative 1.25 to 2 decimal places, and we're done.